Hello everyone and welcome back to this next lecture in the machine simulation series, and this is where we had left off last time, where we were examining how the non-idealities in the magnetic field produced in this induction motor can result not only in a rotational torque but also in a mechanical force that results in vibrations, right? And the reason was pretty simple. We said that even though a vast amount of the magnetic field will be well behaved and will be fairly uniform and will choose the path of least reluctance, which is along the radius, alright, which is along the radius of the cylinder since this is a cross section. And this magnetic flux that chooses this path of least reluctance along the radius will result in a mechanical force that is tangential to the rotor, and therefore it produces a purely rotational torque. However, due to non-idealities in the magnetic field, and which is the case in any physical system because nothing in this world is perfect, there will be a certain amount of magnetic field or a certain amount of lines of magnetic force which will not choose the path of least reluctance. And you could consider this very similar to turbulence in water. Even though water in general will choose the path of least reluctance, due to the chaotic nature of any physical system, there will be some turbulence in the water as well. Alright, there will be undercurrents, there will be other stuff, and in the same way with magnetic field as well, there will be always some amount of non-linearity in the magnetic field, even though the magnetic field is largely uniform, even if it is designed in such a manner. And these non-ideal lines of magnetic force will result in these mechanical force which is not tangential to the rotor, and therefore we can break it down into two projections, one along the tangent and one along the radius. And the one along the tangent will continue to produce a rotational torque, whereas the one along the radius will result in vibrations. So now that we've looked at this, let's just take the ideal case of the mechanical force and try to figure out what the torque will be. So this is what I'll talk about in this lecture, and maybe I'll also touch upon how this method cannot be used in practice. So as before I start the lecture, a little bit of brief background that if you're interested in these kind of video lectures, but you would like something a little more comprehensive, I do have full-length online courses that you can find on my own website, which is pythonpowerelectronics.com. So this website, which is pythonpowerelectronics.com, is the home page of this project, Python Power Electronics, and this is where you'll find almost every information you need about the project. So if you go to these four buttons, and if you click on Learn, it will take you to the list of courses which I have right now. So as of now, I have 5 courses. The very first course is called Simulating Power Electronic Circuits Using Python. And in this, I talk about the basics of how you can use Python and Python Power Electronics to simulate power electronic circuits. The second course I have is called Basics of Digital Signal Processing for Power Engineers. And in this, I talk about how you can use Python and packages such as the SciPy package and the signal package within SciPy to analyze and design filters specifically for power engineering applications. The third course I have is called Simulation of Magnetics for Power Electronics Using Python, and in this I talk about how you can use Python and Python Power Electronics to model basic magnetic components such as inductors, coupled inductors, and transformers. The fourth course I have is called Control Analysis with Python for Grid Connected Converters, and in this I talk about how you can use Python and packages such as the Python control package to analyze and design controllers for power engineering applications with the specific example of a single-phase inverter connected to a single-phase grid. And the very last course I have is called Why Specialize in Power Electronics, and this is a free motivational course which is targeted mainly towards either junior undergraduate students or even high school students who have not yet chosen their domain of specialization. And the purpose of this course is to talk about some of the challenges and opportunities available in power electronics so that they may choose this as their domain of specialization. So all these courses are available on 2 platforms, which is Decibels Labs and Udemy. If you click on any of these buttons, it will take you to the link for the course. The link for this page is available in the description of this video. So if you are interested, please do check it out. So with this, I will get back to the actual lecture. So now, in this case, we had already talked about the basics. That is, we talked about how this mechanical force is produced. And for that, let me go over to my Excel sheet. And in this Excel sheet, we had written some of these basic details. So for example, we had said that the strength of the magnetic field is B, and the current flowing in the rotor conductor is I. And if W is the length of this rotor conductor, then in that case, this force is BIW sine theta, with theta, this TH is theta, is the angle between the magnetic field and the current. Now, for the specific case of a induction motor, and if we are considering the ideal case, not the non-ideal case. Okay? Right now we are looking at the ideal case, and if we say that in the ideal case, the magnetic lines of force will flow through the path of least reluctance along the radius, in that case we can safely say that the angle between the magnetic field and this current in the rotor conductor is going to be 90 degrees. Right? And this is simply because this rotor conductor this is a cross section, and this rotor conductor is actually passing through the screen. So it is, if I look through, let me look at the actual photo of the induction motor. So this is the induction motor, and these you see are the rotor bars. So we are taking a cross section of it. So therefore I am saying that this magnetic field is passing radially through this, produced by the stator, radially through the magnetic field, or rather through the air gap, and therefore it is incident perpendicular to the rotor bar, and therefore the angle between the magnetic field and the current in the ideal case is 90 degrees. So therefore if we go back to this Excel sheet and we look at this formula, we can actually get rid of the sine theta. We don't need the sine theta because it is sine 90 degrees. Theta is 90 degrees. So this leads us to this equation, which is BIW. And here, of course, W is the length of the rotor, right? It is the length of this rotor bar, or you can say, since now there is one little peculiarity which you can look here. These rotor bars are skewed, right? They are not exactly parallel, or rather they are parallel to each other, but they are not exactly along horizontal. They are not horizontal, they are skewed. And there is a reason for that. Usually it is skewed to reduce vibrations, but again, that is a complex concept. Assume now that these rotor bars are not skewed, rather they are horizontal to each other. In that case, the length of this rotor bar is this W which we are talking about, right? Because remember, the magnetic field is incident on the rotor throughout the length. It is not just incident on the rotor at one given point, because the stator conductors are there throughout the stator through these slots, right? There are slots in the stator, right? You can't see them here, but there are slots in the stator through which these conductors pass, and these conductors carry a current and produce a magnetic field. So this magnetic field is present in the air gap throughout the length of the stator, which implies that they are incident on the rotor bars throughout the length of the rotor bars. So which means that the force is equal to B, that is the strength of the magnetic field, multiplied by the current I, multiplied by the length of the rotor bar W. So that is BIW. Now, once we know the force, if by simple physics, right, actually we need now the diagram. If there was a force F, only one force F, acting on any rotation, anything which is capable of rotating along a certain pivot, then in that case the torque will be the force multiplied by the moment arm. So if I say that this radius here of the rotor is R, right? In that case, the torque is F multiplied by R, if F is the mechanical force. So in this case, in this simplified case, right? Remember, this is a simplified case. We are considering all the rotor bars concentrated on just these two slots, right? In that case, since we have two mechanical forces, one at the top and one at the bottom, and they are both producing a force which can rotate it in the same direction, then the total torque is the sum of these two. And if we say that these two are identical, and you can pretty much assume them to be identical, then it's simply twice force multiplied by R. So I can write that as well. So if I say, I'll just write it here. Let me just extend it. So I will say this torque is equal to 2 multiplied by F multiplied by R. And here I need to clarify that R is the radius of the rotor. It has auto moved it up. Okay, R is the radius of the rotor. So we are now saying that we have calculated from basic principles the force and the torque, or rather the torque which is produced by the motor. Now the question you might ask is it possible to calculate B? Yes, it is possible to calculate B. How do we calculate B? We can calculate B by using the information about the magnetic circuit. So for example, if we say that if Ns is the number of stator conductors, right, wrong spelling, number of stator conductors in a particular slot, and these number of stator conductors are carrying a current I, which is the stator current, then in that case the ampere turns produced by the stator slots, so I'm talking about, let me go back here, if there are ns number of stator conductors which are in this slot and they are carrying a current of Is. Again, this is very simplified. Like I said, in reality the slots will be all over the stator, right? So but we are concentrating all of them on these two diametrically opposite stator slots. So for this simplified case, if we say that there are ns number of stator conductors, any number of ns, and these are all carrying a current Is, in that case we can say that the ampere turns will be equal to ns multiplied by Is. And if we know the ampere turns, then in that case we know the flux to be equal to ampere turns divided by reluctance. Now in this case we've already made an assumption. We have already said that in this case this path that the flux will take, let me go up here, the path that the flux will take, as we already said, consists of three parts. There is a path through the stator, there is a path through the air gap, there is a path through the rotor. The path through the stator and the path through the rotor are high permeability paths because the stator and the rotor consists of either laminated iron or some other special alloy. Whichever it is, it will have a very high permeability to magnetic field. On the other hand, air has a much lower permeability to magnetic field. So for example, in general, laminated iron has a relative permeability of 1000, which means it is 1000 times more easy for a magnetic field to pass through iron than through the air. So quite obviously, the biggest blocker to this flow of flux is this air gap. So if I say that this air gap is Lg, right? So if I say that this air gap is Lg, so it's not very easy to read. Lg, actually, let me say Rg. The reason why I don't want to say L, capital L, is because it's usually used for inductance. So Rg is the air gap length. In that case, the reluctance of the air gap, right, if we assume that the flux is flowing along the radius, will be equal to mu 0, which is the permeability of air, multiplied by the length, which is Rg, multiplied by the cross-sectional area. So I'll call this Ag. This cross-sectional area Ag is merely the area of this field which in this air gap. Again, easier to say, let's go over to our diagram here. In this diagram, we can calculate the cross-sectional area as the area of this cylinder, right? of this cylinder through which it passes through. And this cross-sectional area will give us an indication of the area of this area that contributes to the reluctance. So once we know the reluctance, we can calculate the flux. Once we calculate the flux, we can calculate the flux linkages with respect to the rotor. Now here it is the number of rotor turns multiplied by the flux. Right? Simple. Flux linkage of the rotor, maybe I should write it here, psi r. So psi r, again this is probably not very clear. Psi r, I mean you just have to assume like phi, it's simply psi. Psi r is the flux density, and flux density is nothing but the number of turns multiplied by the flux. So this is the flux which links with a certain number of turns. And once you know psi r, it is always possible, and once you know flux, we don't need psi r, we don't need psi r here. Once we have flux, we can calculate the flux density as merely flux divided by this air gap as well. Right? Because it is basically flux multiplied by the air gap through which it passes. It's flux per unit area. So we know B with this formula. I, again, you can calculate it by various ways. You can simulate it as well. But let's say, for example, there was a certain current. In that case, we now know all the parameters that go into calculating the force and therefore into calculating the torque. So this is a way in which we can potentially calculate the torque which is produced by the motor. So this torque here is the torque we are looking at. This is the torque produced. And this torque produced minus the mechanical torque will give us an indication of how this rotor starts moving, the speed that the rotor finally achieves. Now that I have said all this, let me just briefly give you an indication of why no one will do something like this. Now let's go and have a look again at our diagram. We are taking a very simplified case. We are saying that there are only two stator slots. These two stator slots contain all the stator conductors. Similarly, we are saying that all the rotor bars are concentrated at these 2 points diametrically opposite each other on the rotor. Now, if we look at the actual construction of the stator, that's not the case. The stator slots are all over the stator, the entire circumference of the stator. So it's not just diametrically opposite at 2 slots. You want to use the entire stator as much as possible, because that's how you're making the most use of your magnetic material. Because remember, the biggest cost and the biggest bulk is always iron. So therefore you want to use your magnetic material as much as possible. So you're going to try to put as many slots all over the stator and try to utilize your magnetic medium to the maximum. Right? You want to produce a magnetic field which brings the flux towards close to the saturation point, which is at the knee point of your saturation curve, because that's when you utilize your magnetic material to the most. So now, and also the rotor bars are all over the circumference. So now in reality, if we come back here, we are not looking at just these two rotor bars. We are looking at rotor bars all over the circumference. And we are also looking at stator slots all over the circumference, which means that this analysis cannot just be done for these two here, like the way we've done it. We cannot just do it by 2. This will have to be a multiple of the number of slots. So we are looking at the number of slots. Actually, not the number of slots, but the number of rotor bars. And similarly, this flux here will also not just be here, the flux, sorry, no, this one. This flux is not just the flux through one of them, but is the flux through all the stator slots, the stator conductors all over the circumference. Now the question is, how are we going to do this calculation? It is impossible to do it theoretically. It is possible to use some computational techniques to arrive at this number. Right? And there are probably specialized software which do allow you to design machines by actually designing the number of slots, the number of rotor bars, and all other construction details. Right? You can take into account all these construction details to determine how your motor behaves. But theoretically, it is next to impossible for us to actually take all these construction details into account and calculate the entire torque produced because of all these stator slots and all these rotor bars and actually sum them all up. Because we are looking at hundreds of slots and we are looking at probably, even if not hundreds of rotor bars, dozens of rotor bars. So just imagine the amount of calculation we have to do. It may not be possible to even just simply integrate it, because remember, these are discrete slots. These are not slots which are actually placed at infinitesimal points all over the circumference. So a simple integration may not also do. It might actually need a very, very complex form of calculation. So this entire process which I talked about of arriving at how the torque is produced will never be used in practice. What we will use in practice going further is a principle called the conservation of energy. We are going to generate an equation for the torque using the conservation of energy. So the question is, why did I talk about all this? The reason why I talked about all this is because it is very difficult to learn machines just through equations. Right? This process of using the basic laws of physics to figure out how a force is produced on a current carrying, how the force is produced on a rotor, which is a current carrying conductor, how that magnetic field is produced in the first place, how that magnetic field induces a current in the rotor. Let me go through it right from the beginning. We apply a voltage to the stator. The voltage applied to the stator produces the current in the stator. That's how it all begins. You switch on the motor. When you switch on a motor, you are applying a voltage to the stator. When the voltage is applied, a current begins to flow through the stator conductors. The current in the stator conductors produces a magnetic field. You are applying an AC voltage, therefore an AC current will flow. This AC current produces an AC flux, which means it is a varying flux. When a varying flux is associated with another conductor, it induces an EMF. So therefore, this magnetic field produced by the stator will induce an EMF not only within the stator but also in the rotor, any conductor that it associates with. And as you can see, the flux produced by the stator is associating with the rotor. So now an EMF is induced in the rotor, and because this is a squirrel cage induction motor which consists of bars short-circuited on both ends, a current will flow through the stator because it's basically short-circuited bars. If you produce an EMF in a short-circuited system, a current will flow through it. Simple as that. So now this current here, which flows through the rotor, is once again in an external magnetic field. Now you might argue that this current is actually produced by this magnetic field. So they know each other. They are all associated. But that doesn't matter. Okay? It doesn't matter. From the simple laws of physics, if there is a current carrying conductor in an external magnetic field, a mechanical force will be produced on this conductor. And this mechanical force can be determined, the direction of the mechanical force can be determined by Fleming's left-hand rule. Right? And for that we've also seen Fleming's left-hand rule, where we've seen that all you have to do is hold your left hand with the field pointing in the direction of the forefinger pointing in the direction of the magnetic field, the middle finger pointing in the direction of the current, and the thumb will point in the direction of mechanical force. And you have to hold all these three, the thumb, forefinger and middle finger, at 90 degrees to each other. Right? If you do so, then in that case we have the direction of mechanical force. And we found that these are the direction of mechanical force. And we also saw that there could be some non-linearities because of which the mechanical force may not just be purely tangential but could also be a little off. Right? Now, we also saw that this mechanical force can be seen as a result of a vector cross product. Right? It is a vector cross product, and a vector cross product comes with with that equation of BIW sine theta, where theta is the angle between the magnetic field and the current. This is the general equation. And then we boiled it down to this entire equation, and therefore we found that with all these assumptions, we can calculate the torque. Right? So this method of coming up with an equation for the torque for a simplified system using basic laws of physics tells you a lot about how a machine works. And this, in my opinion, is much easier to understand than just using equations. Typically speaking, if you see any book, they will just say the torque is equal to flux multiplied by current. That's all. This gives you no indication or no understanding of what is actually happening inside the machine. How does a machine work? They just say torque is flux multiplied by current, right? But this kind of equations don't really tell you anything about how a machine works. And which is the reason why in this video lecture series, I just wanted to show you that really speaking, to understand how a motor works, all one needs to do is to apply the basic laws of physics. So with this, I'm going to stop this lecture. It's already gotten pretty long. And let me just delete this. In the next lecture, I'm going to talk about the concept of how we are going to use the law of energy conversion to come up with a realistic equation for how the torque is produced. Like I said, realistic, because this entire derivation was for the simplified case, which does not exist in reality, right? And the actual case is too difficult to compute. So therefore, we will come up with a simplified equation for how electrical torque is produced using the law of energy conversion. And that's what I'll talk about in the next lecture. So if you have any doubts, please do message me either on social media or send me an email or place a comment under the video. Otherwise, I will see you next week. Thank you so much and see you soon. Goodbye for now.